university level mathematics is to the mathematics they've seen already, we sort of felt like we wanted to demonstrate to people during the open day, as we normally would, sort of the differences between the university mathematics and A-level mathematics, or potentially any other maths specs you've been looking at if you come from other countries. So, and the way we're going to do this is we're going to look at a couple of step questions, which the basis of the material shouldn't be too much of a stretch from what you've seen already, but sufficiently more challenging and more like the sort of mathematics you'll see at university. So to help you decide whether or not maths is exactly the thing you want to be studying or applying for your degree, that's the point of this session, to give you a taster. So just some technicalities. So we're on Zoom. So I'm here with two other students. One is Kai, who's currently in his 4th year in Cambridge, and the other is Alex, who's currently in his 3rd year. So they're both here as well, and they'll be monitoring the chat function. So Zoom has a chat function, so you should feel free to, at any point, any questions, to message them in the chat. All the messages will go, should in theory, if everything's working properly, should go just to them, so there's not one big global chat which everyone can see. And they can answer your questions live, and also we'll have at the end if we've got time, which we should, a Q&A session with the 3 of us, for which any questions that you have for the Q&A you can ask then, or if there's any big questions we want to ask all together, we'll answer those at the end. Okay, so so as we said before, this will be recorded and put online, so don't worry if you don't catch something in real time. And so the rough plan is you all got sent a question, and so we're going to talk about that for about 15 minutes. Don't worry if you haven't attempted it, we'll just talk through the sort of logical reasoning. Then I'll have another question, which I'll put on the screen, and I'll give you all 5 minutes just to have a think about it. And then we'll we'll talk about that question. And then we should have enough time at the end just for a Q&A. So that's just the rough plan. So since we've already 15 minutes into our allotted time, let's begin. So I should start screen sharing in 3, 2, 1. Cool. So now you should be able to see my screen. So this is the step question which you all got sent. And so the reason we've chosen this question is because in theory it should only require sort of a GCSE level, if you're familiar with the qualification level of mathematics, and just applying that knowledge to a wider, a more difficult question and concept. So in this question, what we have is we're told that we have this definition of so-called integer part, or the floor function of a number x. And so the floor of x is defined to be the greatest integer which is less than or equal to x. And then we were given these examples, i.e., so e.g., the floor of 2 is just 2. The floor of a decimal, 2.9, would be 2. But then also for negative numbers, 1.5, the greatest integer less than or equal to minus 1.5 would be minus 2. So that gives us an idea of what this so-called floor function does. And the floor function you wouldn't have come across most likely in for example, an A-level spec. So this should be new, but you should be able to work with it. And this sort of gives you an idea of, in university, you'll be given new concepts and you've got to get used to them very quickly to be able to digest what they mean and then work with them. Okay, so Then we're told to consider a different function. And this function is defined by f of x being equal to the floor function of x divided by x itself. And a priori, this is a completely new function, so we have no idea what it looks like or what it may do. And the question is all about probing this function and finding out what it sort of looks like and what sort of behavior it has. Okay, so for the first part of the question, part I, we're exactly asked to do that. We're asked to sketch the graph of this function for x in a range between -3 and 3. And x is not equal to 0 because that function wouldn't be defined. So we want to sketch y is equal to f of x for x between 0 and 3. And then x is not equal to 0. So when we look at x, well, x has two parts. X has this 1 over x part, and it also has a 1 over x part. Now, we should all be familiar with, or be able to work out the graph of 1 over x. This is one of the sort of things you'll see in your course, your A-levels or IB or any other qualifications. And so 1 over x looks like this sort of function for x positive, and for x negative, it looks like this. It has asymptotes going towards -infinity and +infinity and 0, depending on the direction. But this floor function we may not have seen before. And if you do lots of step practice, for example, you get used to the feel of the step, and you obviously see some of these concepts multiple times. So there are many step questions which use the floor function. So it's good to do lots of practice so you get used to things. So, and like we said before, we had these examples of what the floor function did for certain numbers. So let's quickly try and sketch what the floor function looks like. And then from that, we should be able to then hopefully deduce what this f of x looks like. So if we draw a set of axes, let's label on some integer values. So we have 1 here, 2 here, and 3 here. 0, -1, -2, extended a bit more, -3, etc. So as we had before, we had these numbers. We knew at 2, this would be equal to 2. So again, I should label my y-axis as well. Extend it a bit. -1, -2, etc. So we had that at 2, it was equal to 2. So we have this point here. And for 2.9 or 2.7, we also had it was equal to 2. And for -1.5, we had it was equal to -2. So that would go down here. So we see that if we're between, say, 2 and 3, we would always expect, well, we always get the value of 2 as the smallest integer. So we expect our graph to look like, well, to be constantly equal to 2 in that range. But at 3, we jump up and we're equal to 3. And so we can demonstrate that is, and this is a good bit of notation if you haven't seen it before, is at 3, we jump up to 3, and we can do like a filled in circle to demonstrate the function takes that value at 3. And we can also do a hollow circle on 3 at that line to demonstrate that it doesn't take the value 2 there. So we do have a jump. And then we can repeat this if we're between 1 and 2. Well, we'd expect the same thing, except now constant equal to 1, and we jump at 2. And then similarly, you can work out that in between 0 and 1, we have this other jump. And then between -1 and 0, we have another jump, and etc., etc. So it looks like a staircase. Okay, so now we know what the function, the floor of x, looks like. So what about our original function, f of x being equal to floor of x over x? Well, in, say, between 1 and 2, we know the floor of x was always equal to 1. So if we broke this up, we could say for x between 1 and 2, we have f of x actually equaling 1 over x, because the floor function in this range was equal to 1. Similarly, for, say, x between 2 and 3, the floor of that number would be equal to 2, and so f of x was equal to 2 over x. And when we do 2 over x as opposed to 1 over x, we've rescaled, so we've multiplied all the y values by 2, and so the graph of 2 over x is higher than the graph of 1 over x. So, and similarly, if we're between any numbers n and n plus 1, x between n and n plus 1, f of x will be equal to n over x. And this is for n greater than or equal to 0. So for n is 0 in particular, when we're between 0 and 1, the floor function was always 0, and thus f would be 0 as well, which is what we see here. For negative n, we have the same thing, except if we're between minus n plus 1 and minus n, then f of x will be equal to minus n plus 1 over x, because here the greatest integer less than x will be equal to minus n plus 1. Yeah, I should have said here n means an integer, so n is equal to 1, 2, 3, ... So integer values. So what we see is that we're just getting rescalings of a 1 over x graph. And in particular, if I look at this line here, so we know f of x was equal to n over x over here. So what were its maximum and minimum values? Well, 1 over x is decreasing in this range, so the maximum value will occur at the smallest value of x, i.e. when n is 1, x is equal to n, sorry. And the biggest value, the smallest value will occur when x is equal to the biggest value, i.e. when x is equal to n plus 1. So what we actually have here is in this range, f of x is always less than or equal to 1 and strictly bigger than n over n plus 1, because we never actually have x is equal to n plus 1 here. Okay, so using this, we can now get a sketch. So let's now draw a big set of axes. And let's label on some points. So 0, 1, 2, 3. I'll extend it a bit more. 4, minus 1, minus 2, minus 3. So what we have is for between 0 and 1, we had that f of x is always equal to 0. So I can draw that in as a red line. And I'm equal to 0 here, but at 1, I'm not equal to 0, and I jump, and I'm actually equal to 1. So I can do a hollow circle, and then a full circle up here at 1. Now in the range between 1 and 2, we had f of x was equal to 1 over x, that's up here. And we also had that if we stick n is 1 into the inequality we have for f, we know that f is between, it starts at 1 and goes down to a half, but doesn't quite reach a half. So the graph would look something along these lines, where it goes down, following on 1 over x graph, and then reaches a value around here, but doesn't take it, and that value is equal to a half. Similarly, then we then jump to 2, and in this range, where f of x means 2 over x, and f of x ranges between 1 and here n is equal to 2, so it's 2 over 2 plus 1, which is equal to 2 over 3. So again, we're decreasing to 2 over 3. So this y value would be 2 over 3. Okay, so that's what the function looks like for x positive. And for x negative, we can do the same thing. And for the sake of time, we can find that we always have this 1 point here where we're starting. And in this case, because it's reversed, we have the graph looking along these lines. So it comes up to a large value, and then it comes down to 1 instead now, and then we jump up to a slightly bigger value, and we come down, and then we jump again, and we go down, and this time we're jumping to smaller and smaller values. And so this value, for example, is equal to 3 over 2, and this value is equal to 4 over 3. So that just comes from sketching f in those different ranges, thinking about, as we did before, the values of f in the range. Okay, so that's the sketch for between x is minus 3 and 3. The second part of the question asks us to consider the line y is equal to 7 over 12 on the graph, and then to solve the equation f of x is equal to 7 over 12. So when we're looking at 7 over 12, we know that this is less than 1. That can be our first observation. And thus on our graph, we are in the range I demonstrate here between the line y is equal to 7 over 2 will be in this range, and thus we're never going to intersect the range for negative x. So when f of x for negative x will never be equal to 7 over 12. So what we have to do is we have to just work out which of the segments over here actually intersects the line 7 over 2, and that will be the case when the minimum value is less than 7 over 12. So when this smallest value here, or this smallest value here, is less than 7 over 12, that means this line segment comes further down than the line 7 over 2, 12, and will intersect. So some quick calculation. We clearly know that 12 is a half, is smaller than 7 over 12, because 7 is bigger than 6. But we also know that 2 over 3, which is equal to 8 over 12, is bigger than 7 over 12. So this tells us that 2 over 3 is bigger, and a half is smaller. So therefore the line, y is 7 over 12, is going to lie in between a half and 2 over 3, i.e. in this green spot where I'm drawing on the graph. And so if we draw it in, it'll look something like this. So this is the line y is 7 over 12. And so in particular, because all the other lines carrying on are bigger, they're all sort of up here and never getting further down, then we'll know that we only get an intersection in the range x is between 1 and 2. And when x is between 1 and 2, we know that f of x is equal to the floor of x over x, which, since x is between 1 and 2, this is just 1 over x. This is for x between 1 and 2. So the only solution to f of x being equal to 7 over 12 is when f of x, 1 over x is equal to 7 over 12, i.e. x is equal to 12 over 7. So that is how we do the first part of the second part. Oh yeah, my value at x is 0 is actually wrong. That's a very good point. Obviously, we can't divide by 0. We removed that from the range. So yeah, that's very right. I should have just had a circle here because we can't take the value of x is equal to 0. So the next part of the question asks us to also solve more equations, f of x being 17 over 24 and f of x being 4 over 3. And we can do this in exactly the same way. We just need to find out where 17 over 24 lies on the graph and where 4 over 3 lies on the graph, and then find which values will hit. And so, for example, 4 over 3, we can already see we've got 4 over 3 on the graph up here. And so the only intersection points will be for that point onwards, which I think I minus 3 over 2. So we should have an intersection in this region, and also no, because my graph is actually wrong. So I think what I meant to have was this part over here should have been a bit higher, actually. I think I've missed a line segment somewhere. Yes, sorry. So this first one should have actually come up to 2. So yeah, I apologize if I make any mistakes doing this live. So this was because that's a hollow circle, sorry. So this was actually going up to 2. I shifted it all down 1, and then this was 3 over 2. And then the next one should have intersected. Yeah, no, what am I doing? Yeah, sorry. So that was 2, and then this one was 3 over 2. Sorry, messing it all up. And then the next one was exactly at 4 over 3. So, but that's a hollow circle, so we don't get an intersection there. So what we do get is we get 3 solutions corresponding to each of the 3 sections here. Okay. So, and then, yeah, so we can do similarly there. The third part about finding the largest root of this equation is we have to just do similar arguments. We know 9 over 10 is smaller than 1, so we're again looking in the range for x positive for solutions, because they're the only places where we have x is less, f of x being less than 1. And then since we know these hollow points over here corresponded to when f was equal to n over n plus 1, we want to find the smallest n, well, the largest n, sorry, for which we have n over n plus 1 is smaller than 9 over 10. And so if we solve this equation, we should find that we need n to be less than 9. Yeah, I'm pretty sure, yeah. Which implies, i.e., n is equal to 8. What is the smallest line segment, well, the smallest region where we would find a solution. And so given that, we would then be looking at when x is between 8 and 9, and so f of x is equal to 8 over x. And so if this is equal to 9 over 10, this would imply that x is equal to 80 over 9. So yeah, I'm going through this relatively quickly, so I make mistakes as you've just seen. So don't worry if you don't follow this in real time. And then the last part, which again is potentially the hardest part, is finding necessary and sufficient conditions in the form of inequalities for the equation f of x equal to c to have exactly n roots. And so we already know what it means to have, well, from the graph, to have exactly 1 root, we could either intersect I'll use a different color. I know the graph is getting now very, very messy. Maybe I could clear it up a bit. I could delete this bit. Delete that bit. Delete this bit up here. To have exactly, delete this as well. To have exactly one root, we would need to be within this region where we do not intersect any of the other line segments, but we do intersect just this first line segment here. Or if we look on the other side, we just want to intersect one of these parts, which would mean that we have to be above this region, so up here. So for example, in that case, we could say to have one solution, we need, so either C being between 2 over 3 or a half strictly, and we can have equality at 2 over 3 because we don't actually take this value up here. The function doesn't take that value. So for positive x, we could have C in that range, but for negative x, equivalently, we could just have lying in this blue region I drew up here, which was when C was bigger than 2. So that's when that line segment was in that region. So for one solution, these were the two inequalities. And similarly, you can argue for n solutions, I need to be within the first n of these line segments, but not the n plus 1th one. Or equivalently over here on the x less than 0, you can be in n of these line segments, but not the n plus 1th one. And so what you should end up with is, in general, we need to have either C less than or equal to n plus 1 over n plus 2, or strictly bigger than n plus 1, or C is between n plus 1 over n and n over n minus 1. So I'm just giving the answers here. I haven't properly justified it, so it's good to go away and actually try and write this down since we have limited time here. But it's important to bear in mind that the question specifically says, give necessary and sufficient conditions. So necessary and sufficient is something you may or may not have come across before. It's also the same as if and only if that more rings of a bell. And this means that you need to provide conditions which are, so we have to prove that if the equation has exactly n roots, then C lies in this range, but also the other way around as well. So if C lies in this range, then the equation has exactly n roots, which is the justification we have sort of from the picture in some sense. So in general, if you ever see something that says necessary or sufficient, you need to prove one direction and the other direction. Okay, so that's what I want to talk about for the first question. If you have any specific questions about this question, feel free to send it in a private message to one of the moderators, either Kai or Alex. The other question which I wanted to bring to this session is the following. So I'll give you a couple of minutes to read over this question and have a few thoughts, and then we'll come back and discuss it quickly before having a mini Q&A. So yeah, feel free to have a think, and in say 2 or 3 minutes we'll talk about it. Okay, so this is step 1, 2004, question 5, in case you want to look it up later. So you can write that down or see it on the video afterwards once the 7 days finished. So this question is very different in flavor. There's no graph sketching, no anything. This is sort of some number theory. So we're told that we can split the positive integers into 5 distinct arithmetic progressions as shown. So A is 1, 6, 11, 16, 2, 7, 12, and B is 2, 7, 12, 17. So we're always adding 5. So we start off nice and simple by asking just to write down a general term in each of the 5 progressions. So clearly in the ones for A, we have them of the form 5n plus 1, for n being 0, 1, 2, etc., because we're always adding 5 and we start at 1. For B, they're of the form 5n plus 2, and for C is a 5n plus 3, and D, this is 5n plus 4, and E is 5n of the form of 5n, except for here we have to have n's between 1, 2, etc., not 0. Okay, then it says, hence prove that the sum of any term in B and any term in C is a term of E. So if we write down a general term in B, this is the form 5n plus 3. And if we add B, sorry, that's 5n plus 2. And if we add any term in C, which is of the form 5m plus 3, it could be another positive integer. When we add these two, we have this is equal to 5 times n plus m plus 5, which again, if we collect, is of the form 5 times n plus m plus 1, which is of the form of E because this is 5 times an integer, a positive integer. So we could say this belongs to E in some senses. This symbol is belongs to, so it belongs to the things in E. Okay, so that's nice and quick. Then the next part asks us to prove that the square of every term in B is a term in D. So if we have something in B, that's of the form 5n plus 2. If we square it, well, we can just expand the brackets. And saving some algebra, this is 25n squared plus 20n plus 4, which if I now collect to write it in the form of something like D, this is the form 5 times 5n squared plus 4n plus 4. So this is some integer, positive integer. So it's 5 times an integer plus 4. So this is in D, which is what we wanted to show. And similarly, we then ask to state and prove a similar claim about the square of every term in C. And so we can do the same thing, 5n plus 3 now squared. And after just doing the algebra, we end up with, if I can do this in my head, this is 5n squared plus 6n plus 9. So this isn't quite of the form of anything we had before, because we got a plus 9 on the end instead. And really we want just a plus 1, 2, 3, or 4. And so this can be dealt with by writing 9 as 4 plus 5, and then combining the 5 in the brackets over there. So this would be equal to 5 times 5n squared plus 6n plus 1 plus 4. And so what we see is, if we took anything in C and squared it, we have 5 times an integer plus 4. So this is in D. So what we have in slightly bad notation, but just to illustrate the point, is we've shown that B squared belongs to D, and c squared belongs to D as well. So if we square something in B or C, we get something in D always. Okay, so now the more daunting part is to show that there do not exist any positive integers x and y such that x squared plus 5y is equal to 243,723. Your first thought should be that the big number is probably an arbitrary number, and so you don't need to really worry about its exact form. But since we're looking at the sequences A, B, C, D, and E, we know that 243,723 is in C because of this plus 3 at the end. It's of the form 5 times something plus 3. Okay. We also know that 5y is in E because it's 5 times something. So, but we don't know anything about x or x squared. So the question becomes, can x squared plus something in E lie in C? And well, we've been calculating squares above. We calculated b squared and c squared. And so there's sort of 5 cases you can consider. So there's, if x was in A, well, let's say it was in B or C, then we would know that x squared is in D by the above. But similarly as to what we did before, if we add something in D to something in E, we can show that this is actually in D again. So in either of these 2 cases, if x was in B or C, then the expression x squared plus 5y would have something in D, add something in E. So this would be in D, not in C. So it cannot equal this big number 243,723. So that was if x was in B or C. Similarly, you can show that if x is in A or D, then x squared is in fact in A again. And in this case, we'd have x squared plus 5y is something in A plus something in E, and it turns out this is in A again, i.e. not in C. So we also can't have, if x is in A, B, C, or D, we cannot have this x squared plus 5y equaling this number. So the final case to consider is if x is in E, but then you can show that if x is in E, then in fact x squared is again in E, and so x squared plus 5y is in something in E plus something else in E, which has to lie in E, which is again not in C. And so no matter the choice, we can never have x squared plus 5y in C. And so there is no solution. So this sort of demonstrates to you how, if you've got something which is where there's only a finite number of cases to consider, which in this case there were 5 cases, if it's in A, B, C, or D, or E, you can just consider each of those cases individually and rule out whether or not something can happen or not. And so in particular, we actually get that this expression can never lie in C. So in particular, we can never have, for example, 5 squared plus 3y equaling 3 or 18 or any number which has a remainder of 3 when divided by 5. The last part of the question, I won't talk about in detail, but you can do in a very similar way, except this time we have powers of 4. So I'll give you a hint to consider if x is in A, B, C, D, or E, where can x to the 4 lie? Which of these can it lie in? And by considering the cases, you should be able to prove that there are no positive integers such that this other expression holds as well. Okay, so I think so I should say that this question is an example of something you'll come across in your university degree in mathematics, which is called modulo arithmetic. So if you want to look up a modulo arithmetic, it's something which is very accessible to people who are sort of thinking about applying for a maths degree. You should, with limited mathematical background, you should be able to read about it. So I would encourage you to do so because it's quite an interesting topic and quite useful. Yeah, so I think we'll stop talking about the step questions there, and we'll go back to the Zoom room, and then we'll start answering people's questions if we've been sent any. So let's go back. I'll stop sharing my screen. And okay, I think I'm back now, and the other co-hosts can come in with their video if they wish. And so if you've got any questions now, feel free to send them on the chat or to one of us and we will answer them. If not, then I guess we'll if not, then we'll probably end the session there, but we should have some questions. So I'm just looking at the chat now.
Yeah, we've got a question about what our interviews were like. Paul, do you want to start?
Yeah, so my interview, so I should say that I didn't actually say who I was at the beginning. So yeah, so I'm currently a PhD student in the maths department who came to Cambridge back in 2014. So my interview was quite a long way ago, but I remember we had 2 interviews, and I thought the first one was loosely based on mechanics because I had done a fair bit of mechanics, and I thought that went relatively well. And then my second one I thought went very badly, and that was the end of the Cambridge dream. So so it's amazing how you can perceive things one way, but they actually turn out a different way. I don't know if Kai, if you had any different experiences.
Yes, I mean, I had just the one interview. I had a pre-interview test, and then I took the test into the interview, and we discussed those questions and my answers. So I didn't think it went well either. I think that's maybe quite a common thing, that it seemed to have gone all right in the end. But yeah, basically we're just talking about a whole range of maths, from sort of couple of mechanics questions to stuff like probability, graph sketching. So it's just a wide range of topics. But yeah, I didn't think it went that well, but must have went all right in the end. How about you, Alex?
There we go. My phone's working now. Quite similar, really. So in terms of pragmatic details, what happens is, this might depend on college, but for Clare, which is where I am, you go and then you have 2 interviews and they ask you some questions about maths. And so you try and do the maths and show them how you like to think. So I was terrified about my interviews, actually. My first one, I got several bits of maths wrong. And then my second one, I just sat there and they asked me to work out what a particular polynomial looked like. And I started saying, okay, well, if this is really big, then it might be positive. Turns out they wanted you to factorize it. But in stuff like that, the advantage of the interviews is that you can start showing them how you think. If they ask you questions that you don't know the answer to, you shouldn't freeze up, and you can just tell them what you're going through. We've got another question about how do you learn to do these questions in 30 minutes? Quite simply, I'd like to say it's a lot of practice. When I started my step revision before my first interview, I tried to do a paper 1 question, and I didn't manage to make any progress. I tried to do a different paper 1 question, again, no progress. So I was really quite terrified about how to go through step. After the interview, after I got my offer, I started revising for step more seriously. And then just by doing loads of past papers, you can get to where you can start doing these in a more reasonable span of time.
I think we've probably only got time for one more question. So I think we had one in the chat about if you're happy that you went to Cambridge and if you wished you went to another university. I mean, I'd have to say I'm quite glad I went to Cambridge. I mean, there's always times while I'm here that I complain about it, but I think everyone's going to have that at some point when you've got a deadline the next day and you've got stuff to do for it. But no, at the end of the day, I think there's no other place I'd rather be to study maths for a university. But I suppose wherever you go, as long as you enjoy it, that's the main thing. Enjoy doing maths, enjoy your experience. I don't know, Paul, you got anything to add to that? You've been here for a while.
Yeah. I mean, I don't have any regrets about coming to Cambridge. The course is very good and it prepares you very well. One of the things about Cambridge, in particular, the college system, is that it does give you a lot of individual opportunity, which is still going to be there at other universities, but I think is more easily accessible in Cambridge because of having like over 20 different colleges where everything's split up into. Each college has its own opportunities, and so you're not competing necessarily against the whole university for an opportunity, but with the people in your college or just in your subject within your college. So there's a lot of opportunity for you to enhance your CV and things like that. I do wish that people had potentially given me a bit more information about other international universities in different countries, not just the UK. I mean, my school didn't provide any support or even consider this. So, but that's not so much a regret. It's more just I potentially wish that I had been a bit more looked at things a bit more in detail about outside the UK. So, but yeah, I'm not sure if Alex, do you have anything else to say?
I think overall, I'd definitely say there's been positives, there's been negatives. Perhaps the one thing I'd like to say, I personally think I've really enjoyed my time at Cambridge, but I also think I would have enjoyed being somewhere else. I think the important part when you go to a university, sort of beyond the basic questions of, do I have the grades to get in? Am I going to be able to keep up? Sort of, these are the, sorry, these are the usual questions that you might want to ask. But on top of that, I would recommend asking, am I going to be able to, in this university, do what I would like to do? Perhaps you're interested in doing straight maths all day. In that case, look for a university where they have a single focus program. Cambridge has an excellent one of these. Maybe you'd like to do sort of American style liberal arts, in which case you might want to look elsewhere. So really sort of ask, what do I want out of this university experience?
They're all very good points. So I don't think we have any more questions from what I'm aware. In which case, I think we should probably end the session because we're running over time. So in which case, I thank you all for joining. I hope this was useful. Yeah, I'm glad that we have one thank you, another thank you. So yeah, and then I wish you all the best of luck in your applications, and I'm sure whatever happens, it'll be the best thing, and I hope you enjoy it and the application progress. Okay, well, see you all soon, maybe.